Okay. All right. Welcome, guys. If you haven't gotten one yet, there are cookies in the back and napkins, so you can go take some of those. So this is a 3D printing workshop. This time we're going to be doing Inventor. So for those of you who came last time, we talked about Tinkercad, which is a nice tool for like hobbyist projects and the occasional like small model. But Inventor is another tool made by the same company, Autodesk, and this tool has a lot more features, a lot more powerful, but the design techniques are a little bit different. So we'll first go over the same stuff we did last time in terms of like what 3D printing is and how it kind of fits into manufacturing, and then we'll talk about Inventor itself. So let's dive right in. So how is stuff made today? So I'm just going to run through this. We have hand making. Like this was a traditional method for putting things together. So you would, you have like people who sewed clothes or worked looms and stuff like that. And there are a lot of advantages and disadvantages to each of these different manufacturing techniques. In the case of hand making, it takes a long time, but it's very customizable. Like you can make it different every time. There's also tool manufacturing, like casting, cutting, stamping, weaving. Any machines that are basically designed to make one particular thing. So most assembly lines in factories are of this kind of form. And this is really neat because you can get high volume and high rate and high repeatability in your parts, but you can't really change it much because once you build the machine to build a certain kind of part, it's kind of stuck doing that thing. Now there's something that's kind of in between, which is CNC automated machining. And this is like milling and laser cutting, and 3D printing also kind of falls into this category. And this is where you have high repeatability because there's high precision in the movement of the parts. Basically, it's a computer-controlled machine that has a tool of some kind that moves around and makes a part out of material. So CNC, like mills, for example, are a subtractive process. You have a solid block of material, and you cut out stuff to leave behind the part that you want. And 3D printing is the other way around. It's an additive process. So you start with nothing, and you extrude plastic, or you bind resin or something like that, and that produces the part that you want. And with CNC automation, you have high repeatability, high precision. It's slower, but it's very customizable because every time you make a part, you can adjust some parameters here and there, and it can be a little bit different. So 3D printing fits into that category, but it can be even considered a category in and of itself. And it affords a lot of things that traditional manufacturing techniques, including CNC machining, don't really offer you. And some examples of that we'll get to in a sec. But basically, the process of 3D printing is converting a digital something into a real something. So all of these objects that you see up here, and you guys are free to take these and play with them. These are all parts that were designed in Inventor and then printed on the printer. So there are models that I'll give you guys at the end of this presentation that you can look at, and you can take them apart and see exactly how all those things were designed. Huh? What? Yeah, it doesn't work. What doesn't work? No. Oh, that's this thing. Yeah. No, don't worry about it. Okay. Yeah. So we're converting digital stuff into real stuff, and this allows us that same customizability. Basically, every time we print something, we can change something about it. And printers are really fast, and so we'll see what that allows us to do later. But there are some things that you can't really make any other way than using a technique like 3D printing. If you can imagine, like, if you've ever seen like a Turner's cube, it's basically a bunch of nested cubes that are cut out by using a circular drill to make circular pockets in the sides of a cube, and you tunnel down, and eventually what you end up with is a bunch of cubes inside of each other, like going all the way down to smaller and smaller cubes. Something like that is very, very difficult to do with machining. Like it's actually a machining practice problem, pretty much. Like you give people who are learning to be machinists this problem of making this object, and it's very difficult. But with a 3D printer, like that shape is easy. Like you can just put the file into this machine, and it will just go and make it. Now you can also do things like embed things inside of entirely closed volumes. So if you want a shell, for example, and inside that shell, like say it's like an egg shell, inside that shell you have some very, very detailed part, like a tiny model of a chicken or something like that. You can do that. Because what the printer does is it builds things in layers. So at every point in the construction of this model, it's looking at a cross-section of what's inside. And so it can put fine detail into this volume and close it around it. And you can't really do that with any other kind of machining. Like you can't use a mill that uses a tool that has to dig into the material. You can't go inside and then somehow put back the material that you cut away on the outside. So 3D printing is unique in that way. And generally 3D printing is additive. There are, I guess you could consider certain kinds of CNC milling to be 3D printing, but yeah. So this is the general workflow. You have a computer, design something, put it on the printer, and a part pops out. So real quick, it's fast, it's cheap, it's heavily customizable, like we said. And this is the key right here. It allows for iterative design and prototyping. So what exactly does that mean? Can anybody tell me what they think that means? So basically, it's so cheap. Like each one of those parts on the table right there is on the order of like $1, okay, or even less, maybe. Some like the smaller parts, that carabiner is probably like 10 cents. So in terms of price to make something, it costs almost nothing. So you can design something and build it using a 3D printer and expect it not to work. And it's OK. It's no big deal. Because what you do is you try it out. It doesn't work. OK, you throw it out. You print a new one. It's no big deal. And you can do that as many times as you want until you run out of money, which is never. So so you can see here some examples of things that were made on more advanced 3D printers. This one does plastic, but there are printers that will print things in metal. And you can see they make very detailed parts, like this geometric thing over here. Imagine trying to make that using traditional tooling. Imagine having to make that by hand, for example. If that was a block of wood and you had to carve that out of it, like, good luck, man. Like, I definitely wouldn't want to do that. And so you could make those very repeatably and also for relatively low cost in terms of like what it would cost somebody to, if you asked them to make something like that. Maybe the first time they printed that, the holes weren't the right size. Well, it's no big deal. They can just print another one. Now, there are some limitations to 3D printing. Can anybody point out a limitation of this printer? Yeah.
It's like this big.
Yes, size is an important limitation. What else? Yeah.
Material.
Yeah, material. That's actually the first one that I had, materials and colors. So this guy right now has a spool of orange PLA loaded inside. So PLA is the same material that milk cartons are made out of, but it's plastic. So you can only print in plastic. And on top of that, like we only have one color in there right now. You can't do multicolor prints. I mean, you can, but it requires like printing part of it in one color and then unloading and then putting a new spool in, and it's a huge pain. So this is fixed material, fixed color. Dimensions, like you said. Certain shapes are difficult to make. So there are shapes that lend themselves well to 3D printing and shapes that lend themselves poorly to 3D printing. And we'll talk about that in a sec when we're doing some design stuff. Any other ideas about limitations here? So that you can only print something so big, right? But you can also only print something so small, right? Yeah, feature sizes. So this is an issue that has to do with the extruder. And this is something that you want to keep in mind. When you're designing parts for 3D printing, know the limitations of your machine. Because you might say, like, oh, I want to make a tiny robot fly or something like that. And you're probably not going to be able to print all that fine detail on a machine like this. Now, if you had an SLA printer, for example, like the Form 1, which uses photo-curable resin and a UV projector to make the parts, you could get very, very high precision parts, like down to like 5, 10 micron precision. This thing, the minimum layer height is 50 microns. So that's 1/2 of a tenth of a millimeter. But that's still not that small when you're working with like tiny gears and stuff like that. Any other ideas about what the limitations of the machine might be? OK, that was kind of a hard one. It's not always reliable. And here are some examples of ways that it's not reliable. Like that model on the upper right there, that's some complicated geometric shape. And with the really thin features like that, it's a bunch of little sticks, basically, like that are made into this I guess it looks like an icosahedron or something. But those thin sticks don't afford much support because the printer has to print up, basically. So it puts like layer after layer of material. And with really thin things like that, they could have started drooping. And then once it's drooping, it's trying to print into midair. And then it starts making all that stringy stuff. And then it looked like I got a little bit towards the top when things kind of like came back together. But yeah, in the middle, yeah. And then I guess that was supposed to be an owl or something on the lower right there, but definitely didn't turn out that way. And that dude's head is like in like 4 pieces. So yeah, so printers can be kind of wonky. Final thing we're going to talk about here, CAD for 3D printing. So this is what we're doing right now. So you need to kind of understand what the geometry of the parts are, what the limitations of the printer are in order to be able to be effective at 3D printing. So if you look at the image on the right, you can see basically how this printer makes parts. So what it does is it has a little nozzle that extrudes plastic, and it's hot, so don't touch it. But basically, it melts plastic, and then it draws it into these little strings, okay? And then by repeatedly placing strings next to each other, it makes layers. And then by repeatedly stacking layers, it makes a part. So if you look at that's supposed to be like a cross-section of a half of a sphere, a hemisphere, or something like that. So you can see that hemisphere is made up of stacks of circles. And each circle is made up of a crisscrossing pattern of lines. So can you guys kind of visualize how that works? Now, one thing that you want to avoid in 3D printing, and this is where whether it's good for 3D printing or not comes in, you want to avoid overhangs. So an overhang is anywhere in your part where you have something that doesn't have anything below it, so anything that doesn't have support. So if you look at that image in the lower right, you can see that the model on the right with the X next to it, that has an overhang. That top bar there is just floating in midair. So when the printer goes to make that, what it's going to do is it's going to start at the bottom, and it's going to print little rectangles to form the bottom half of that part. So it's going to print little rectangles like this, okay? And it'll keep stacking those rectangles until it gets to here. And then it'll start printing squares over here and get up to here. And then when it gets up to here, it's going to try to print this thing. What it's going to do is it's going to bring the nozzle over here and try to start printing a rectangle, and it's just going to squirt plastic out into midair, and then it's going to droop. Now, the thing is that the plastic is a little bit viscous, and it does cool pretty quickly. So what will happen eventually is that pile of droopy plastic will eventually stack up to the right height, and it will start printing like an OK rectangle after that. But then when you get the part out the printer, you're going to have to cut out all the material, and there's going to be missing volume there, and you don't want that. Now, there is a way to overcome this, which is you can design it like this, where basically the overhang or the angle is steep enough that each layer has just enough support from the one below it to be OK. So basically, when it puts this next layer on, it's overhanging by just a little bit. But because it's only like half a millimeter or so, it's OK. But if the angle gets too shallow, then it will droop the same way. So this is one way you can solve the problem. The other way you can solve the problem is by adding support material. So support material is where the printer will actually add extra plastic that you didn't design into the model, in places where it is necessary to support the part. So it'll basically put like fluffy stuff in here to hold it up when it prints it. And the final thing that you want to think about is orientation. So the part on the right could actually have been printed successfully if the designer laid it flat on the build platform, right? Because this part is basically a flat plane extruded this way, and all these faces are perpendicular to each other. So if it laid it on its side, it would be OK. So that's another way you could solve the problem, is by changing orientation. Now, that presents some interesting problems, and so this is what I'm talking about with the overhang. Like, this is OK, this is kind of OK, that's definitely not OK. Orientation is important. So remember how the part is made up of layers of material, and the adhesion between the layers is not very good. Okay, that is like the point of failure in the part. So the strand of filament itself is much stronger lengthwise than the adhesion between layers. Okay, so if you were to design a wrench, say for example, and you printed the wrench so that it's standing up, like standing vertically on the build platform, you would end up with layers that are oriented this way. Can everybody see that? And if you printed the wrench flat on the build platform, you would end up with layers that are oriented this way, right? Now, if I were to use this wrench to try to turn a bolt or a nut, I'm applying a lot of torque on the handle. And that torque is forcing the layers apart. So this wrench will fail. Whereas this wrench, in this case, I'm working with the length of the strands of plastic that make up the layers, in which case I have a benefit in strength in that axis. Now, yeah, I guess wrenches don't really have any forces that are along this direction. But if for some reason you put the wrench in a vise and then tried pulling on it really hard, you could get the layers to separate. But the idea is that if you're, you need to think about what your part is doing, like what function it serves, and try to visualize what the layer orientation needs to be in order to give you the best strength in your part. So are there any questions about that? All right, cool. OK, so Inventor. Let's talk about that. So Inventor is a sketch-based modeling program. It is geometric, so basically all of the geometry in your model is based on like primitives. So you have like squares and rectangles and circles and things like that, arcs, curves. But the idea is that you have a series of sketches, which are profiles of your model, and you perform operations on them to pull them into 3D space. So if you want to make a cube, for example, you start with a square, and you extrude the square along the third dimension, and you end up with a cube. All right? And it's parametric, meaning that all of the dimensions in your model are defined by you. And one of the really neat things about the way that this modeling program works, and that it's a constructive modeling program. It uses mathematical relationships between parts of the geometry in order to end up with the final form. This means that you can go back in time pretty much. And I'll show this in a second. You can modify parameters that you set previously in your design process, and the model will update to reflect those changes. And I'll show you how that works. And finally, like Inventor is much more powerful than this. It has lots of features. And one feature that I particularly like is the table-based design. So if you have a model that is like a generic copy of something, like you have a bolt, for example, and this bolt has different lengths. Say you have like a 3-inch bolt and a 4-inch bolt and a 5-inch bolt. You can design that part to take data from an Excel spreadsheet, and you can add rows to that Excel spreadsheet that will define parameters for this model in different forms, and you can automatically generate all the copies of the model for those different table rows. And that's just like one of the many, many features that are built into this program. And I'll address that probably in the next 3D printing workshop, if anybody's interested. So what I urge you to do now is if you have Inventor on your computer, please go to that URL and download the example models. These will help you kind of understand how things are put together. So you can pick up one of the models at the table here and compare them with the models that are online. So I'll just leave this up here for a few moments. And by a show of hands, does anybody still need it, or has everybody typed it in? OK. There we go. Run 2. OK. So start page. So we're going to go to New, which is upper left here. Sorry, go to the Inventor icon, and then go to New, and say Create a new file from the list of templates. And this will pull up this little window here. And I like to work in the metric system. So I go to, under templates, there's a metric folder. And if you select standard millimeter IPart, that's your units in your project part will be in millimeters. If you prefer to work in inches for whatever reason, you can choose that there. But I personally like to do this. So what I'll do is I'll go templates metric and then select standard millimeter IPart. So it takes a little while to load. And then what it should do is it should pop up a new model for me. OK, great. All right. So now we have an empty workspace. So on the left-hand side, you can see the hierarchy view. This is where all of the features in your part will show up in this little tree view here, right here. And this area right here is the view window that'll show you your model. And you have some navigation options here. So there's this cube up here, and you can click and drag on it to rotate the view. You can also use right-click, or sorry, what did I just do? I just close my model. So if you right-click and drag, it uses these little stupid little like gesture things. I don't like those. So if you use middle click is pan, and then if you hold shift and middle click and drag, that does rotate. And then if you ever lose sight of your model, there's a little spyglass with a file inside of it. That's the recenter view. So that'll normalize the viewing window. OK, so I'm going to save this now so we can change the settings. So go ahead and go to the eye in the corner and hit save. And it'll prompt you for a location to save it. And I'm going to put it in the workshops folder. So that's here. And I'll save it over this guy. OK. So now that we have that, let's configure our export settings. So when you guys submit your models, I don't have to fiddle around with them. So go to the eye and then export, and just hover over it, and then click on CAD format. Okay. And in here, in the save as type thing, switch it to STL, which is the format that the slicing software for the printer understands. And then finally go to options and change the units to millimeter. So they should be centimeter by default, but yeah, if you change it to millimeter, that'll save me some trouble. And then when you're done with that, just hit OK, and then you can close out of this because you're already done saving it. OK, so is everybody with me? Anybody need a second to catch up? All right, cool. So the first thing we're going to look at now is the sketch. So the place where you start in Inventor is with a sketch, which is a drawing of, like I said, like a profile of your model. So we'll start off by just doing something really simple, a cube. Okay. So the first step is to start a 2D sketch. So you click up here, and it opens up this little plane chooser. So these are the 3 coordinate planes. You also have 3 coordinate axes, which are these lines here, and then your origin. All of these can be found under the origin folder in the hierarchy view. Now, we're going to go with the XZ plane. So the y-axis is the vertical axis in this coordinate system. So we'll go to the XZ plane so we can draw the base of our cube. So just click on the plane, and it will open up the sketch editor. Now, I will place a rectangle. And I'm going to choose a different option for how to draw it. So this option allows you to draw like corner to corner, like that. But we want to center it. I just press Control-Z to undo. You want to center it in the view. So we'll center it on the origin. The way we'll do that is by selecting the 2-point center option. And the first point is the center, and the second point is a corner. And you can see here, as I move around this point, that I have 2 little input boxes that show me what the dimensions are on this part. So right now, I'll just click somewhere and leave it. And now to fully constrain it, so right now it's green. The lines are green, which means it is not constrained. The model has not had all of its dimensions, and basically it has degrees of freedom. You can move it in some way. And I can demonstrate this. If I escape out of there, I can pull on this little guy and pull it around. You can see that it moves around. So we don't want this, because this means that there's indeterminacy in our model. So we want to lock it to a certain dimension, and we'll do that by clicking the dimension tool up here. And now what you can do is you can select a feature, like this edge right here, and pull up. So you click and pull up like this, and then click again to place it. And now I can edit this and say that I want this to be exactly 20 millimeters. And now this length right here is constrained to 20 millimeters. Likewise, I can constrain the other edge. And this time, instead of entering an absolute value, what I'm going to do is I'm going to enter a ratio with the other dimension. So in order to do this, I will select the other dimension while I'm in the editor, and that pulls up D0. So D0 is the name of this dimension right here. And then I will say that I want it to be D0 divided by 2. So this is now 10 millimeters. And you can see that it writes it as fx colon 10, and that means 10 millimeters, and it's defined by a function. So now we will close out of this. So I guess it's not going to be a cube. It's going to be a rectangular prism. But yeah. So we'll close out of that by hitting the finish box in the upper right. Anybody need time to catch up, or are we all good?
How do you change from inches to centimeters and millimeters?
Have you already opened a part?
No.
OK. So what you can do is from up here in the Inventor toolbar, click on this little guy. You go to New, create a new file from list of templates. Under the templates folder dropdown in this view, click on metric, and then choose standard millimeter IPart. All right. OK. So any other questions right now, or are we all good? So notice that these lines have changed to purple, and that means that now this entire box is fully constrained. All of its dimensions are specified. And you might be wondering, like, OK, so the width and the height are specified, but what about the location? Now, if you remember, when we created this rectangle, we placed the center of the rectangle at the origin. And the origin is a point whose location is defined as 0, 0, 0. So this is now fully constrained. And like I said before, that plane that we were working in, the XZ plane, is right here. It's in the origin view. And you can make any of these visible. So right now, they're all marked not visible. But if you want to see the planes, you can do it like that. OK, so just for demonstration's sake, we'll name this. And we'll call it prism base. OK. So now that we have this guy, we're going to turn him into a prism. And the way we do that is by using the 3D model ribbon. So before we were in the sketch ribbon, these are tools that are only available to us when we're working in a sketch. Now we're in the 3D model ribbon. And these are tools that allow us to manipulate three-dimensional features. So what we'll do is we'll extrude this shape into 3 dimensions. So we'll start by clicking on extrude and selecting, well, it automatically selects because it's the only available thing to select. But if you had to select it manually, you use the profile picker. So you click on this little box, and if you hold Shift, it allows you to deselect. So I can deselect this guy. And if I'm choosing the profile and I hover over it, you can see it turns a little bit whiter. And that indicates that I'm selecting this region here. Now, if I had multiple regions in my sketch, multiple closed loops, I could select any of them to extrude. But because there's only one closed loop here, meaning that all these edges are connected in a loop, there's only one closed loop, so I can only select that one. All right, and now you can either use this little arrow to pull on the volume and change its size, or you can enter a number for the distance to extrude into this box. So I'll make this 10 millimeters. Now, as before, all of the dimensions are available to edit or to use in functions from anywhere. So I could even make this d0 divided by 2 again, and it would be OK. So if you guys want to be able to go and edit parameters globally, under the Manage tab, there is this FX box. If you click on that, that brings up the parameters view. And you can see here all of the parameters that make up my model. So I have this parameter here, d0, which is this length here. We have d1, which is defined as d0 divided by 2. This is units, 2 units. So this is basically the no dimension. Yeah. So like you have like millimeter as a dimension, inches as a dimension. This is what it uses when you're indicating like a count, like how many iterations of something, or a factor of some kind. So this d1 is this edge length here. And then the final edge length is d2, which is this vertical edge length. And you might be wondering what d3 is. D3 is the taper of the extrusion. So if I wanted to make this extrusion not straight, if I wanted to make it more like a trapezoidal kind of shape, I could make this, say, 15 degrees. And that causes it to flare out as it comes up. So this is saying that the angle between this face and the vertical from this face is 15 degrees. But we'll leave that 0 for now. You can also change the names of the dimensions. So if you like to name things accordingly, we could call this width. We could call this length. Although I guess actually it should be length. Length, width, and height. And we'll call this taper. OK. So there it is. We have a prism. And you might be wondering how I'm doing this. I have a 3D mouse, which allows me to rotate the model. So yeah, that's why you're getting that funky effect. You can also change the view perspective. So right now, this is projected in something called orthographic projection, which is where objects do not change size based on distance. So you'll notice that I can orient this model to face the front plane, and it looks like a square. Now, this is contrary to your daily perception, because usually if you look at an object like this head-on, the face in the back would be smaller than the face in the front, although it would be occluded. So if you had a different shape, you might be able to see that there's an effect due to perspective. Like I'm shorter at this distance than I am if I'm right next to you. Now you can change it to look perspective in this little drop down if you switch it to perspective, and now you'll see that the model is drawn as if it were in the real world. But you'll probably find it more useful to work in orthographic projection because you don't have a dependence on distance for sizes of things, and it helps you better gauge what the relationships are in terms of size between things. OK, so now that we have this, we can continue manipulating it. And we can add some other features. Like, let's say that we wanted to round these corners. So how will we do that? So we have a tool up here called Fillet, which allows us to do just that. So we can select this tool. And in this box here, it'll tell us like which edges we've selected so far. But basically, in the view window, you just pick an edge like this, and it'll round the corner like that. Boom, 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 boom. OK. Like that. All right. And if we apply it, we can also change the radius of the fillet. So right now, it's at a 2 millimeter radius. We could change that to 4 millimeters. And you can see that it becomes much deeper. And again, at any time, we can change any of these dimensions. So let's say that we actually did want it to be a cube originally, and we want the fillet to stay exactly the way it is right now. What we can do is we can go back to the Manage tab, and go to the parameters, and say, you know what? This should really be 10 millimeters. And this guy should also be 10 millimeters. And this guy should be 10 millimeters. And there we have it. So the model has been updated to reflect the changes in dimension. OK? Any questions about that?
What would happen if you change your radius larger than you had before?
So you'll have problems solving the model. So basically, any changes that you apply, we can actually demonstrate that. So if I made this fillet radius, say, some ridiculous value like 20 millimeters. OK, that actually worked. But that is not very useful. Let's go let's see, how else could we do? Really absurd. OK, that doesn't seem to be demonstrating my point. Let's do something different. See, how can we get this to break? OK. If we made this negative. No? OK. Yeah, I'm having trouble demonstrating it right now. If I pull up a different model, I can show it breaking. But basically what it'll do is it'll pop up a dialog box telling you that it failed to solve some component of your model. That can be due to various different reasons. Usually it's due to some feature that you based a design on somewhere in your hierarchy being no longer available. So for example, if you have two lines that were intersecting as a result of some dimension, and you change that dimension so they're no longer intersecting, and you would use the point of their intersection to define some other feature, then it would break. Sure, yeah, exactly. So if I make the sketch here, you can use project geometry, which is this tool right here, to select things from your model and put them into the sketch plane. So the sketch plane is on the top of this face here, and I could project this square into that plane, and now I have it to work with. So if I finish this model now and say, oops, change that back to 10. OK. So if I now extrude that face, like that, and go back and change the fillet so that there is no longer that square there. So make it, say, 20. Wow, that's interesting. Never seen that happen before. Well, clearly it's broken, but it didn't complain about it for some reason. Yeah. So in this case, that feature disappeared, and I'm actually kind of curious as to why it's still there. Oh, interesting. That geometry is actually still there. No, it's not. OK, yeah. So you can see here that the color of this has changed to pink. That means that geometry is no longer available. But for some reason, it didn't complain about it. It just broke it. What?
Maybe when you define the function for it, it kind of converts that to a constant value in space, and then it just uses that.
Yeah. Right here. OK, so we have an up. So this little shock icon is update. So it'll do a global update and refresh all parameters. So I think that this will probably get it to break. Or not. OK. OK, yeah. So what happened is when it changes to pink like that, it means that whatever geometry it was referencing has disappeared. and as a result, it's broken. And I actually suspect that if we change it back to 4 millimeters, that it will probably still be screwed up, but we can see it might be okay. Okay, so it's okay. So yeah, so there are limitations to this. Obviously, geometry in the three-dimensional part is dependent on all these parameters. So if you change a parameter and as a result something disappears, your model can break in really fantastic and horrible ways. One thing that I will warn you about is that fillets are especially finicky. I have found myself in situations where I had a very complicated set of fillets and I adjusted a dimension and Inventor will just crash on you. So be really careful about that. I've only seen it happen when you enter the fillet to edit it. So if it complains to you and tells you that the fillet dimension or the fillet parameters are somehow screwed up, save your model immediately because it's going to crash. Yeah. You can go back. You can undo to undo whatever change you did. So to undo, you just press Control Z. There's also these undo and redo buttons up here, and Control Y will redo. But yeah, like just be aware that Inventor does crash. So it's a good idea to save your work often, and you can kind of just get that reflex, Control S, and you'll be good. OK, so let's go and look at a more complicated model because we're not going to be able to get much done here. So if we go, pull up the carabiner model. So I don't know, where is the carabiner right now? It's still up here. So if you guys want, you can pass this around and compare it to what you see on screen. There you go. So for those of you who don't know what a carabiner is, it's one of these guys. So I use it to hold my keys. They're used a lot in rock climbing and stuff like that to fasten ropes and things. But basically the idea is that you have this hook-shaped object, and there's a spring-loaded clasp that you can press on that'll hinge. And in this case, the way that this actually behaves like a spring is that the plastic that the printer extrudes is flexible a little bit. And so what we do is we distribute the bending of the plastic over this little squiggly. So the squiggle has lots of curves in it. And so when you bend that squiggle, the angle, the bend basically is distributed amongst all of those little curves. So each curve will only bend a few degrees, but the total bend will be on the order of like 20 or 30 degrees. It is meant to open. I printed it a little bit too small, so the tolerance on the opening is a little bit too tight, so it fused together. If we had a pair of pliers, we could probably pry it apart. But yeah. So let's look at how this model was made, and this will give you a better idea of the sorts of things you can do in Inventor. So I didn't talk about sketch constraints, and we'll look at that first. So in this sketch, this is the base sketch for the carabiner. And you can see here that there is this little slot in the sketch. That's not being used right now in the current geometry. And that's due to the way that this extrusion is defined. But basically, the idea here is that you have two sets of concentric circles. So these were drawn with the arc tool. So the arc is a section of a circle, and there is a format of the arc tool which allows you to do a center point and then define 2 points along the curve. So if you click on this, you can select the center and then choose 2 points, and you get an arc like that. So what I did is I did 2 arcs. 1 arc, 2 arcs. And their dimensions are the inner arc is defined as 5 millimeters from the outer arc. So this dimension right here specifies the difference in radii of these 2 arcs. And the outer arc is defined as 35 millimeters in diameter. So if we go to inspect, we can see what the dimension of this one is. So it should be 12.5. Right? So that's under inspect. Use the distance tool, the little measuring tool, and you can find out what the radius is, measure the length of this right here at 36.01, so on. OK. So let's talk about constraints. So we have these 2 sets of concentric circles, one on the left and one on the right. And we have some lines here, which are both tangent and coincident with these circles. So basically, the endpoints of these line segments lie on the circle. And the way that you do that, I'll demonstrate that real quick, is let's say we have 2 circles like this. 1, 2. We can draw the line by clicking the first point here and the second point here. Now, what's actually happened here is this geometry, this point here, is now constrained to this circle. So if I adjust the size of this circle, you can see that the point moves with it. All right? So if you right-click and say Show All Constraints, you can see here that there is a coincident constraint here. All right? And this defines that this line lies on this point, and this constraint defines that that point then lies on the circle. And you can actually delete these constraints, and you should be able to free the line from the circle. All right? We can put it back using this little toolbar up here. This is the constraints toolbox, and you can select coincident, select the point, and then place it back on the circle. All right? Any questions about that?
So how you do that? Like how to change to the ultimate this shape?
OK, so the last thing is it is coincident now, but it's not tangent. So the constraint for that is this one right here, the tangent constraint. So we select that, click on the curve, or click on the line, and then click on the curve. And now this line is both coincident and tangent to the circle. So now it lies on the circle like that. And we can do the same thing with the other side. And now we have basically what looks like a rubber band stretched around the circles. And we do the same thing for the other side. All right? And we end up with this shape here. OK. So that's what allows us to do these lines here. So we had a set of inner circles and a set of outer circles, and we used the constraints to place these lines, and then we used the dimension tool to constrain everything until everything turns purple. So you want your sketch to be purple. If there's anything green in there, that means it's not constrained. And one good way to figure out what the degree of freedom is to grab it with the cursor. So hit escape to make sure you're not using any tool, and then use the cursor to just try and pull on it. So for example, if I were to remove this dimension right here, you can see all this stuff change to green. And to figure out why it's green, I'll just try pulling on something and see what happens. So that didn't seem to do anything. What about this point over here? No. There we go. OK, so if I pull on this point, I can see, oh, OK, so the length isn't constrained. So if I put that dimension back in, it's now constrained. All right? So that's a good way to figure out where there's a problem. Now, there are a lot of constraints up here, and it's kind of just a matter of playing with them to see how they work. You can also hover over them, and it'll show you these neat little animations of how to use them and kind of what they do. So for example, to make these 2 points right here, the centers of these circles lie on the x-axis, I use the horizontal constraint. So what this does is it says that 2 points or a line should be horizontal with respect to the coordinate system. So they should lie along the x-axis. So you can see here that that's what these constraints are right here. They're horizontal constraints. And this constraint right here is a horizontal constraint defined between those 2 points. So it means that the line that intersects both of those points needs to be horizontal with respect to the reference frame. Does that make sense? So if I were to delete this, I can now hinge this entire thing. Oop. I can now, oop, why? I'll hide. There we go. Yeah, so I can now basically hinge this entire blob around the center of the other circle. OK? And it flails around a little bit because the solver is not perfect, but yeah. OK. Any questions about that sketch? OK, so I think the last thing that we'll address is the repetitions in the 3D features. So you'll notice here that this squiggly shape looks very similar, right? There's basically a single pattern, which is this little section here repeated, however many, 5 times. So in order to make that happen, I actually did not go and draw every single one of these little curves. What I did is I drew one curve, and then I used a special tool called the rectangular tiling tool, or rectangular pattern, to place it multiple times. So we'll look at how that looks. So we can scroll through the hierarchy, and it'll highlight stuff as we go. This is the one that defines that shape. So we'll expand it and look at the sketch. So the sketch was defined on the face of the extrusion from before. So we had that sketch and we extruded it. And don't mind this little slot here. This was done by some other sketches. But essentially, this is the sketch that we saw the first time extruded into space along the z-axis. And that produces this little profile. Now, what I did is, in order to make this sketch here, you can right-click on any face and say New Sketch. And it will place a work plane and then a sketch on that face. OK? So in this sketch, the first step was to project the geometry for this part of the carabiner into the work plane. So that was done using project geometry. And you can see that it's yellow because it has a constraint related to the shape of the stuff underneath it. So for example, if I wanted to add this outer curve to the sketch plane, I could say project geometry, select the curve, and now it's in the plane to work with. All right? So the first thing was to place these 3 lines in the sketch plane. The next step was to draw these 4 circles that have a very peculiar relationship in that there are these inner circles here and these outer circles. And these outer circles are tangent to lines that are also tangent to the inner circles. And these lines are perpendicular to the axis of this block here. So that's a lot of words. But the idea is that there is some connection of these profiles that produces the cut that I was talking about, or that we saw earlier. And that profile is, if you follow my mouse, we come along this curve, we wrap around this way, and come out this way. That's one half of the squiggle. And the other half of the squiggle is over here. We come around this curve this way, dip into here, come around this way, and pop out here. So if we were to take these regions here, these 2 regions, and cut them from the model, we'll have one part of the squiggle that we want. So that's exactly what we did. So here, you can see that this extrusion is defined as a cut. So we have a join operation, which will add material. So that looks like, I don't know why that's not letting me do that. To distance. So you can see here that this is what join looks like. That means we're adding material, and it's colored slightly green to indicate that we're adding. There's also cut. And we cut all. And what all means is that any geometry that intersects the cut as it extrudes through will be removed. So there's nothing underneath the model. Like this goes off to infinity. There's nothing there. So the only part that is actually cutting is this part. And we hit OK. Uh-oh. So this is what I'm talking about. It'll pop up little stuff like this, and it'll tell you like, oh no, like something bad happened, and you'll know, OK, whatever. Sure, fine. OK. So the last step here is to make this part of the model copy multiple times along this length. And what I just did there is I moved the end of part up. So this little marker is a virtual like feature, and what it really means is the last thing in the hierarchy that you want to see. So the hierarchy is built chronologically. Things that are at the top of the hierarchy were made first. Things that are at the bottom of the hierarchy were made last. So you can move this end of part around in your model to kind of see like what the history was. And this allows you to kind of play with things and make changes further back in the history. And likewise, you can disable individual features. So let's say I didn't want to have this print. You can say right-click on this and say suppress, and that'll remove it from the model. So we'll suppress those. OK. And there's a third guy in there, and we can suppress that too. OK. So now there we go. All right. So this is what we're interested in. We're interested in making this copy multiple times, and the final step to do that is we add a rectangular pattern. So what I'll do is I'll do it again. So basically what you do is you go up in 3D model and you select this icon right here, rectangular pattern, and you select the feature that you want to pattern. So you can select it in the hierarchy like this, or you can select it in the view. Doesn't matter. I'll select it in the hierarchy. So I click on this, and then you need to select a direction to perform the pattern in. So we'll click on this select box to choose the primary direction. And any line will do. So find a line in your model, and it just so happens that this line is in the direction we want. So we'll click on this. And it's going the wrong way, so we'll flip it with this little icon here, flip. And now we need to make sure that the spacing is right. So I don't actually remember what the dimension was. We can go back and look. So it looks like the distance between repetitions should be, so we're going to go from here. Oh boy, what is this? You know what, screw it. I'm just gonna go, I'm gonna cheat. I'm gonna look at what I did before. So it looks like what I did was 4.75 millimeters. OK, yeah, that would take me so long to calculate. All right, anyway, the idea was that the point that on the circle that contacts here should be the same distance as the next point. I calculated this looking at the radii of the circles. But this could be just as easily defined as a function of the radii. If I knew what the function was that mapped the choice of radii to the distance along the pattern, I could add that here. So anyway, I chose 5 units, so it's copied 5 times. We could do it, say, 6 times just as easily, and it would add an extra copy of the pattern here. And then we say OK. And yeah. And that's how we do that. Any questions on that? Any questions in general? Because we're hitting end of time here. So I'm going to give you guys the submission link. For those of you who don't have Inventor, you guys can download it over the weekend and work on this stuff. The submission guidelines are basically design something that you want to have printed, and you'll submit your STL. So like before, the way you export that is, like I showed you, you go up here, go to Export, CAD Format, choose STL here. Make sure that your options are set to millimeter in the units. And this video will be on the website, so you guys can follow it there. And then you just save it from here wherever you want. And then you'll put that in Google Drive, somewhere on your Google Drive. If you don't have one, make an account. Basically, I just need a place where I can download it. So you put it in your Google Drive and then mark it public. And I'll add a note on how to do that. And then send me the link in the submission form. And again, like last time, I will pick 5 models to be printed. I'll print them out, and then I'll email you with whatever email you put in the form, and you can come pick it up. So so that's that. So any questions before I put up the submission link?
How do we get Inventor?
So there's a document that went out with the IEEE email on this workshop. I don't know if you got it, but basically there's a, let's see if I can find it here. There's this guide. Here we go. This guide that I wrote up. And this will explain how to sign up for an educational account on the Autodesk website and get the copy of the software installed. It'll only run on Windows, so if you have a Mac or something, you can install a virtual machine, and that's covered in this top bit here.
On our YouTube channel, and I'll post it on the UCLA IEEE group, so that you can use that to reference.
Okay, yeah. So I guess all this stuff will appear in the description of the YouTube video. So yeah.